Today we are going to talk about the spring circuit problem. We are group 5. Our system consists of pairs of spring and mass connecting in series. There are two kinds of force involved in this question: restoring force of spring and gravitational force. However, to simplify the question, we just set the original point to equilibrium position with gravitational force. Then the gravity will be cancelled out. Now let's look at a fraction of the circuit. Since the gravity had been cancelled out, for a mass there are only two forces from the adjacent springs, which equals to the spring constants multiplied the elongation. The acceleration will be the sum of the forces divided by mass. We can represent it in matrix form. So for three pairs of spring and masses, x double prime equals to a multiplied x. Since we know that x should be sinusoidal, the eigenvalues equals to minus omega squared. Omega is the angular frequencies. For three eigenvalues, we also have three eigenvectors. From the result we have calculated, the function should be in this form, with constants c1, c2, c3, phase phi1, phi2, phi3, determined by initial position and velocity. It's a second-order differential equation with three variables, so there are 6 constants for 6 initial conditions. But why should we solve this question? Because applying Fourier series, we can get any periodic function we want. Fourier series states that any periodic function can be represented by a sum of constants, sine and cosine with different frequencies. The reason is that we can establish a vector space with 1, sine and cosine with different frequencies as our basis vectors. An inner product can be the integral of the product of the two functions in a period. Also, any two basis vectors are orthogonal, which can be proved by product to sum formula. By this property, we can get the coefficient for linear combination by inner products. But actually, the Dirichlet condition, which is these three conditions, should hold to apply Fourier series. Now, for example, if we try to obtain a square wave with low level equals to minus 1, high level equals to 1, duty cycle 50%, angular frequency equals to 1, we calculate the inner product. The product of 1 and sine are 0, so the coefficients of these terms are 0. And this is the product of cosine, so this will be the coefficient for the cosine terms. We can represent it in sigma form. Take the first three terms, and this will be the theoretical waveform. Then we can let the omega and the coefficient and phase equals to these numbers, and we can obtain the square wave we want, but just approximately, because we just take the first three terms. But actually, we are just going to perform two pairs of spring and mass instead of three, for a reason that the eigenvalues of this 3x3 matrix is so complicated that we try to solve this equation in MATLAB, but the computer just keep lagging. We can't get the result. So we have no choice but to do the two pairs of spring and mass instead. And this is the initial condition we calculated in MATLAB.